Let's set the scene. You're in a data science interview and the interviewer says, "You're measuring average transaction values, but your data looks skewed. How can you still make statistical inferences with confidence?" If that question makes your brain pause for a second, you're not alone. This is where one of statistics' most powerful ideas comes in, the Central Limit Theorem, or CLT. Here's the intuition behind it, and I'll keep it simple. The Central Limit Theorem says that no matter how messy or skewed your original data is, if you take enough random samples and calculate their means, those sample means will form a normal, bell-shaped curve as the sample size grows. So even if your original population is weird, exponential, uniform, or totally irregular, the distribution of sample means smooths out and becomes normal. That's the magic. It's what allows us to make confident predictions, run hypothesis tests, and use statistical inference, even when real-world data looks nothing like a perfect bell curve. Now let's talk about why the Central Limit Theorem is such a big deal in real data science work. In practice, this theorem powers almost every statistical technique you use, from ABB testing to confidence intervals, to comparing models and metrics. Take ABB testing as an example. Even if individual user behaviors are unpredictable, one user clicks 100 times, another not at all, the average conversion rates across thousands of users still form a near-perfect normal curve. That's the Central Limit Theorem in action. It's what makes your p-values and confidence intervals valid in the first place. And here's how a strong interview answer would sound. The Central Limit Theorem explains that when we repeatedly take samples and compute their means, those means approximate a normal distribution, regardless of how the original data looks, as long as the sample size is large enough. This is crucial because it allows us to use statistical tests and confidence intervals reliably, even when the raw data itself isn't normal. That's the answer that tells an interviewer. You don't just know the definition, you understand why it matters in ABC testing, model validation, and nearly every decision-making process driven by data.